Webb is fully operational again. Rolls-Royce is building a nuclear reactor for the moon. And the space debris worst case scenario almost happened. All this and more in this week's episode of Space Bites. Last week we talked about the James Webb Space Telescope and how a software glitch took down the near-infrared imager and slitless spectrograph, or NIRISS. And this is the second time that an instrument on board JWST had gone offline, so we were nervous to see another instrument go offline for some period of time. But good news, it was actually very short. So engineers were able to dig into the problem and figure out what had gone wrong. And the answer was a galactic cosmic ray. And these are particles with enormous amounts of energy that are being blasted out from an unknown source. Astronomers still aren't entirely sure. I mean, it probably has something to do with black holes or maybe magnetars or pulsar. Who knows what it is? But it is a very high particle accelerator that is hurling these particles out. And from time to time, they hit spacecraft and flip bits and cause various problems with the hardware on board the spacecraft. So the answer was, and I'm sure many of you watching this could have just given the space agency an answer, was to turn it off and turn it back on again. And so once they rebooted the software on the computer, it went back into normal operations. They tested everything out, made sure everything was fine. And on January 31st, they resumed operations with NIRISS. So a short delay. Thanks, universe, for causing some problems with Webb, but now everything is back and operational. Whew. Rolls-Royce is building a nuclear reactor on the moon. Another week, another nuclear reactor in space news. And this week we got detailed information about a new nuclear reactor that Rolls-Royce is building. Now, they're the car company, but they also build aircraft engines and work on a lot of other aerospace applications. And they announced actually about a year ago that they were working on a micro-nuclear reactor. This is something that would be brought to the surface of the moon to help assist with the power generating needs of a base or space station or spacecraft or so on. And in fact, the microreactor that they're proposing would actually have a dual use. It could both be used as propulsion, so as a nuclear thermal propulsion system, but it could also be used for providing power and electricity. And this is important because when you're on the moon, you spend 2 weeks in darkness and then 2 weeks in the sunlight. And so when you're in the darkness, you need some form of power generating that can get you through that long lunar night. Now, you're probably okay if you're going to be down at the South Pole of the moon and you're going to be in the eternally lit mountains that are at the South Pole. But if you want just a general application to be on the moon, you're going to need some kind of nuclear power. Like batteries just can't last that period of time. Solar panels won't work in the darkness, so you need a nuclear reactor. Their plan is to miniaturize the technology to a reactor that can provide sort of a range from watts to megawatts of energy. And so we're still waiting to see what the final design is going to look like, but they actually shared a whole bunch of information on their website about different configurations and how they could be used for propulsion and baseload power and everything in between, and as well as these sort of hybrid ideas of both propulsion and electricity generation. So we'll keep you posted when a prototype is actually functional. They're hoping by the end of the 2020s to have something operational. We almost had the worst case scenario in space debris. I saw this really unsettling tweet chain that came out from a company called Leo Labs just a couple of days ago. Now, Leo Labs has built a really sophisticated space debris tracking system. They are tracking tens of thousands of pieces of space debris at various altitudes and watching to see how close they come on various orbits. And the folks at Leo Labs posted a series of tweets talking about one really close call that they saw. So the collision almost happened with a Russian SL-8 rocket booster and a Cosmos 2361 satellite. Now, both of them are defunct, so it's been many years since they were operational, and they came within 6 meters of each other. That's close. And that's not the worst part. The worst part is that they came that close at an altitude of almost 1,000 kilometers. When you think about Starlink, you think about the International Space Station, like low Earth orbit, like you're looking at 500 kilometers of altitude. Although objects are coming very close all the time at that lower altitude, if they crash, cause debris, if one of the satellites fails, there's so much air resistance at that lower altitude that the satellite will come back to Earth with just in a couple of years. Like the Starlinks, they have to run their krypton ion engines nonstop to keep them from deorbiting just within a couple of years. But when you go all the way up to about 1,000 kilometers, there's almost no atmospheric resistance at that point. And so anything that's up there is going to continue orbiting for decades. And so to have these two really large objects almost crash into each other, the potential is that they would release an enormous amount of debris that would fill this slot in space, and it would take effectively decades for it to rain back down and be deorbited by the Earth's atmosphere. And this would create a hazard for anyone who wants to, I don't know, leave the Earth and go to the moon or Mars or anywhere. It would be a very bad day, and it feels kind of inevitable at some point. Now, according to Leo Labs, they're tracking 160 of these SL8 rocket bodies. There's many other objects in the same orbit. It was quite heavily used by Russia. But these objects are slowly sinking in their altitude, and so over those decades, they will come from that 1,000 kilometers altitude down until they're in the same kind of range that the International Space Station is in and that the Starlinks are in. So all of this space debris that's up there is a problem that is already bad, and it's going to be getting worse just from all the legacy launches that have already happened, not to mention all of the future stuff that we're going to be launching. But I think just in general, that idea, when you think about tens of thousands of satellites in low Earth orbit, that's a problem, but it's not as bad as the satellites that are at that much higher orbit at the 1,000 kilometer range and above. The higher you go, the longer the debris stays in orbit around the Earth. But maybe we've got a solution. We got an announcement this week that the European Space Agency has tested a drag augmentation deorbiting system, or ADO, on their Ion satellite carrier. This is sort of like a solar sail that was deployed by this spacecraft. It had a small 10 centimeter by 10 centimeter by 10 centimeter little cube of mylar, and then it popped this thing open and it turned into about a 4-meter drag sail that was attached to the satellite. And because of this much larger surface area, the atmospheric drag increased. And it's estimated that normally the satellite would come back down to Earth in about 4 to 5 years, but thanks to the drag sail, it's only going to take about 15 months. And the European Space Agency is pretty serious about zero space debris in the future. And their objective is that if you're going to launch something into orbit, you have to have a mechanism for being able to bring it back down again when the mission is over. And so this drag sail attached to a satellite is a great way to be able to do that for relatively inexpensively. You can imagine every space system being launched into orbit in the future having one of these just as required by law, and when their mission is over, they have to pop this drag sail and deorbit themselves back into the atmosphere and clean up the space environment. So we've got the risk, the scary risk of potential collisions, but on the other hand, we've got some pretty serious movement into solutions to decrease the amount of space debris that we'll see in the future. Destroying rubble pile asteroids is practically impossible. Thanks to all these cool missions to asteroids, we're learning that more and more of the asteroids aren't these like giant monolithic chunks of rock, but they're actually these rubble pile asteroids, where they're just a collection of rock and debris that is in a rough circular-ish shape. So most of the smaller asteroids that we see are these rubble pile asteroids, and they are the result of collisions between asteroids. Two asteroids crash into each other, they break up into a big cloud of debris, and then the mutual gravity of all that debris pulls it back together just into this loose, rocky pile. And they're much less dense than the monolithic asteroids, and they're almost spongy, where we know that, say, when OSIRIS-REx was collecting its sample from asteroid Bennu, it sunk into the surface of the asteroid. If it didn't have a way to sort of retro-rocket jump itself back off, it would have just sunk into the surface of asteroid Bennu. You know, they have some very strange properties because they really don't have any craters on them. So they're resurfaced, remodeled every time they have a close call with another asteroid. Every time they crash into one, they get broken up into this cloud of debris, and then the debris pulls itself back down together and the asteroid is renewed. And so when we think about how we're going to mitigate and stop asteroid impacts coming to Earth, the idea is like, let's send a nuclear missile, let's blow them up. Well, like, you just blow it up and it'll just puff out and then pull itself back together again, and the asteroid is still on its way. And we saw the test with the DART mission blasting into Dimorphos, and it was able to give it a kick and in fact take advantage of the fact that the asteroid is made of debris to gain additional thrust. So that seems to be the way. And now it seems like, okay, many more of the asteroids than we knew before are these rubble piles, and they are impossible to destroy. You have to push them out of the way, and that's going to require a different strategy for dealing with these asteroids when we know that they're on a collision course with Earth. Of course, I did an interview with Dr. Adam Frank as a way that we could use these rubble pile asteroids to turn them into some kind of habitat in space. Put a bag around them, spin them up, and so they turn into the cylinder that you can live on the inside, maybe get some kind of gravity. It's a really cool idea, and I think you'll really enjoy the interview. Now, many of you watch these news segments that I do every week, but this is only just one part of the content that I create here on the YouTube channel. The other big one that I do is the questions and answer shows. And I do these every Monday at 5 p.m. Pacific time, but then we edit them down and put in a lot of other visuals, and we release those once a week on Tuesdays. And a lot of the people who sign on to become a patron of our channel, they say that the question shows are their favorite part of everything that we do. So if you've been watching the Space Bites, the news, but you haven't watched the question shows, you should watch the question shows. We've done over 200 of them. There's been thousands of questions that we've answered. We've got a playlist. You can go and check them all out. And of course, if you have questions, I will answer them. Come join the show live, and I answer many, many questions on each one of those shows. They're a lot of fun, and there actually should be a link to the next episode somewhere here on my channel. You can click on the notification bell, and then of course, YouTube will absolutely let you know when the show is about to begin. So definitely go and check that out. Speaking of the question show, we've had a lot of people ask questions about POP3 stars. These are, of course, the first stars in the universe, the ones that formed out of the primordial hydrogen and helium that was present after the Big Bang. How big were these stars? How powerful were their supernovae? How long did they live? We don't know. Nobody has ever been able to see these stars directly. And that's partly because they happened so early on in the universe, it's beyond the reach of even the James Webb Space Telescope. Maybe it'll be able to gather some evidence of POP3 stars, but so far, nothing is really known about them specifically. No observations have been made, only theoretical knowledge. Now, how big could they be? Now, current stars really max out at about 100 times the mass of the sun. You can get more massive stars, but they have to collide with each other. Just a regular star forming about 100 times the mass of the sun. And that's because as gas is coming into the star, it heats up, and eventually there's so much temperature and heat and radiation pushing outward that it stops any future gas from flowing in and joining the star. But at the beginning of the universe, there were probably these large blobs of relatively cold gas. And as a shock wave from, say, a nearby supernova passed through the region, this gas would collapse down almost instantly. And you wouldn't get that in-between phase where the hot gas would try to prevent other material from falling in. And so according to new simulations, some of these clusters of gas could be 100,000 times the mass of the sun. And it could very well be that those first stars, those population 3 stars, were tens of thousands, maybe even 100,000 times the mass of the sun. Can you imagine what kind of star that would be? It must have lived a very short life and detonated as a supernova that just like boggles the imagination. Think about when a normal massive star explodes as a supernova. It's in the tens of times the mass of the sun. And so one that was 100,000 times the mass of the sun, that's amazing. And maybe there's some kind of link between these population 3 stars and then the early germs of the supermassive black holes, which are continually surprising astronomers at like how quickly they grow and how big they've gotten already early on in the universe. So it's an interesting theory simulation, but we still need new techniques, new telescopes to be able to finally see these POP3 stars. Check out this 12-year exoplanet time lapse. We know about thousands of confirmed exoplanets with probably 10,000 planets awaiting confirmation. So we know about a lot of planets, but the problem is that all of the observations that have been made are indirect, right? You have the radial velocity method, where you are measuring the movement of the star based on the gravitational pull of the planet. And so you infer the mass of the planet that is orbiting the star, and you figure out what its rotation period is. There's the transit method, where you can watch how the light of a star dims as the planet is passing in front of the star. You can also get a sense of the atmosphere. You can measure the radius of the planet, as well as how long it takes to go around the star. But the new exciting way that we're going to be finding exoplanets is with direct imaging. And this is exactly what it sounds like. And astronomers have actually been doing this for more than a decade. There's a very famous extrasolar planet system called HR 8799. And this star is only about 140 light years away and has about 1.5 times the mass of the sun. And it's bright enough that you can actually see it with the unaided eye if you know where to look and you've got really nice dark skies. And astronomers have known that it has many planets orbiting around it. The current count is 4, but there must be more in there. And the configuration of the star and the configuration of its planets are like face on. And so we get this perfect view. And the planets are so far away from the star that you can actually image them separately from the brightness of the star. And so you've got this perfect system for being able to do this direct observation of the planets. And so the astronomers who have been doing these observations, they've been taking images on a regular basis over the course of 12 years. And so they've taken all of those images and they've turned it into this time lapse. And it's like I've been tracking this series of this planet and the time lapses and watching these, and they've just been getting longer and longer and longer. And now there's 12 years of data. And like, it's hard to describe how exciting this is, that you are watching actual planets orbiting around a star in another system. Now, they're nothing like the solar system. They're big. The closest planet in this probably takes about 45 years to go around the star. So like that's longer than Saturn does. And the farthest one takes about 500 years to orbit. So that's like longer than Pluto. But still, real planets orbiting a star, and you're just like looking at a video time lapse of this. And you know, this will be remembered, I think, as the first nascent age of us being able to do exoplanet imaging. But when the really big space telescopes come online, when the extremely large telescope comes online, more and more of these kinds of observations will be possible. And most planetary systems, right, for us to be able to detect them with our current methods, they have to be lined up. It has to be star, planet, Earth, perfectly lined up. Very few planets are perfectly lined up with their star from our perspective. How many planets out there are orbiting face on or some angle of face on? All of them. And so direct imaging will be the way that will let us see the rest of the planets and find out how common planets are around other stars. It's tricky work, but it's going to be so worth it. And the new tools are coming online in just a couple of years, and this will be commonplace. God, I love this time lapse. Measuring the mass of a star for the first time. I've mentioned many times that all of the goodness in astronomy leads back to the Gaia Space Telescope. This is the mission from the European Space Agency that is tracking the location of over 1 billion stars in the Milky Way. It's found white dwarfs and pulsars and even a black hole or two. It's found exoplanets, but most importantly, it's tracking the location and motion of so many stars in the Milky Way. Astronomers were watching the motion of a very nearby white dwarf called LAWD 37, LAWD 37. And it's only about 15 light years away from us. And astronomers could tell that it was going to be passing directly in front of a background star at a very specific time. So they turned their telescopes on the white dwarf and watched as it passed in front of the background star, and watched the gravitational lensing as the gravity of the white dwarf distorted the light from the background star. And based on this, they were able to essentially measure the gravitational influence and measure the mass of the white dwarf itself by how the light curved and changed and distorted as it passed in front of that star. And this is actually a monumental discovery because this is the first time that astronomers have ever measured the mass of a star directly, other than the sun. And when you measure the mass of an object in space, it's actually tricky because you can only measure them through their movements when they have things that orbit them. So for example, if you saw a planet just alone by itself, it would be really hard to measure the mass of that planet. Once it's got a moon and you can measure how long it takes for that moon to go around it, then you can measure the mass of the planet and the moon and get your calculation. This is the equations, the gift that Newton gave us. He figured out the laws of gravitation, and you can use the same technique. How massive is that asteroid? Nobody knows. How massive is that asteroid with a tiny moon? You can get the number precisely. You can measure the mass of galaxies and galaxy clusters. As long as things are orbiting other things, you can measure their mass. But in this case, astronomers were able to measure the mass of this solitary white dwarf. And they found that it was about 56% of the mass of the sun. And they knew that it was about 1.15 billion years old. And from all of this information, was able to sort of confirm various theories about the evolution of white dwarfs. Like after a star like our sun dies, it puffs out its outer layers, becomes a red giant, and then compacts down and becomes a white dwarf. And then it cools down eventually to the background temperature of the universe. And we see lots of white dwarfs out there at different temperatures. And now we know what the mass is. So it's an amazing discovery. And hopefully there'll be other situations where you'll get stars passing in front of other stars and they're able to measure the mass with gravitational lensing. You don't need some object orbiting around it to get at the mass. It'll probably be very rare, but very useful because it can give you such a precise number. All right, those are all the stories that we had today. Of course, we put more information in the show notes down below so you can follow either our story on Universe Today or the original source. You can get more information. You can also get even more space news in my weekly email newsletter. I send it out every Friday to more than 60,000 people. I write every word, there are no ads, and it's absolutely free. Subscribe at universetoday.com/newsletter. You can also subscribe to the Universe Today podcast. There you can find an audio version of all of our news, interviews, and Q&As, as well as exclusive content. Subscribe at universetoday.com/podcast or search for Universe Today on Apple Podcasts, Spotify, or wherever you get your podcasts. A huge thanks to everyone who supports us on Patreon and helps us stay independent. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to George, Jeremy Mattern, Jordan Young, Tim Whalen, Dave Verbeoff, Josh Schultz, and Andrew M. Gross, who support us at the Master of the Universe level. All your support means the universe to us. All right, all the news that we had for today. See you next week.